Today's lecture will have two parts to it. The first part of our lecture today will be on Q problems. Up till now, one of our initial concentrations in our ice types of problems have always been 0. And if you have an initial concentration that starts at 0, it's quite easy for you to determine that whatever side that includes that 0 will be the positive change, and the opposite side will be the negative change. Now, a Q problem is when you start with initial concentrations of everything. You have all reactants, all products, all have an initial concentration. At that point, then you have to do a separate calculation called a Q calculation to be able to determine what the change will be. In other words, when you get to the change line in your ice chart, which side will be a positive change and which side will be a negative change. So you can see our steps that we'll do. We'll take the initial concentrations of all species and solve the equilibrium expression, the KEQ expression, the law of mass action. But instead of solving for KEQ, since that's defined at equilibrium, we're going to solve for the letter Q. And we compare Q to KEQ. Circle, highlight, underline, whatever you need to do for those two statements there. When Q is larger than KEQ, you'll shift to the reactants. When Q is smaller than KEQ, you'll shift to the products. Let's give you an example of how this works in your notes. We have a reaction there. Carbon dioxide is in equilibrium with carbon monoxide and oxygen gas. If we start with 2.0 molar of all species in a 2-liter flask, which direction will it shift? So we have our ice chart. If we were to set up an ice chart for this, okay, we'd have I, C, E, and you have 2.0 molar, so that would be our initial concentration for all three. So this is the point at which you would get and say, okay, wait a minute. I have initial concentrations of all of them, therefore I can't easily determine what the change is. So you'd write the law of mass action, the KEQ expression, have the concentration of carbon monoxide squared, concentration of O2 over the concentration of CO2, which is squared, and we're going to use these initial concentrations and plug them into there. Now, because it's not at equilibrium, we can no longer call it KEQ. So we call it Q when we plug in the initial concentrations. We have 2.0 squared times 2.0, 2.0 squared. So obviously the 2.0 squares cancel each other out, and we're left with just Q equals 2.0. So then we go back to the statements that we have up at the top of the screen here. Our KEQ value, which is given in the problem, is 1.6 times 10 to the minus 7. Therefore, Q is larger than KEQ. Since Q is larger than KEQ, we're going to see a shift left. And that's all this problem is requiring. If, for some reason, the problem asks you to go further, then you would recognize that that would be increase, that would be decrease, and then you would continue on with the problem. Since our problem only asks us to solve for which direction the reaction is shift, we're going to stop there and move on to our second type of problem that we have today. Our second type of problem that we have today is a large KEQ problem. You've probably noticed a trend at this point when all the ice problems that we've done up to this point have all been a small KEQ value, which means the reaction favors the reactants, and X has been a very small number throughout the ice problems we've done up to this point. Now, the next example is how to handle when you have a large KEQ value. That means you're going to have a lot of your material shift to the product side, and X is going to end up being a large number. If X is a large number, then we can't, unfortunately, make the assumption anymore, and we are forced to do the quadratic equation. So, give you an example of what this would look like. We have 2 moles of hydrogen gas mixed with 1 mole of iodine gas in a 0.50 liter container to produce hydroiodic gas. At this temperature, the KEQ value is 50. So seeing a large KEQ value right there means you're going to have a lot of material shift from the reactant side to the product side. X will be a large number. So first thing I'm going to do is write an equation. We're going to have H2 plus I2 in equilibrium with 2HI. We're going to then solve for our initial concentrations. Our initial concentration of H2 is the 2.0 moles of gas divided by the 0.50 liters, and that's going to give me 4.0 molar. Then my initial concentration of the iodine gas is going to be 1.0 moles divided by 0.50 liters, and that will give me an initial concentration of 2.0 molar. I'm now ready to go ahead and set up my ice chart. We're going to have a concentration of H2, concentration of I2, concentration of HI, then we're going to have I, C, and E. Our initial concentration, we have 4.0 molar here, 2.0 molar here, and 0 molar here, which means that's going to increase by 2x, and both of those are going to decrease by x. My three statements, 4.0 minus x, 2.0 minus x, and this one will just simply be 2x. Now I'm ready to go ahead and write my KEQ expression. KEQ is going to be the concentration of the product, HI, squared divided by the concentrations of H2 times the concentration of I2. I'm now ready to plug in my KEQ value and my three statements in the E row of our chart. So we're going to have 50, then we're going to have 2x squared over 4.0 minus x, and 2.0 minus x. Once again, because there's a large KEQ value, at this point I would consider making the assumption. The issue is that if I make the assumption both this minus x and this minus x drop out of the problem. The issue being x is going to be a large number. So if I remove those two minus x's, that's going to throw my number off significantly. And I will end up with way, way over a 5% error when I were to go ahead and check my assumption. Therefore, I'm going to have to actually go ahead and solve the quadratic equation here. First step, I'm going to go ahead and do my FOIL for my denominator, the front, outer, inner, and last. So we're going to end up with 4x squared on the top. Then we have 8.0 minus 4.0x minus 2.0x plus x squared, and that will equal 50. I'm going to combine the two x's together, so then I'm going to have 4x squared over 8.0 minus 6.0x plus 2x, and that's going to equal 50. I'm then going to move the denominator to the other side, so I'll end up with 50 times 8.0 minus 6.0x plus 2x, and that's going to equal 4x squared. I will now distribute the 50 to the 3 in parentheses, so we end up with a 400 as our first term, minus 300x as our second term, and 50x squared as our third term, and then 4x squared on the other side. I will then move the 4x squared over to the other side, so I end up with 400 minus 300x plus 46x squared equals 0. I'm going to rearrange this so it's written in standard format. We have 46x squared minus 300x plus 400, and that equals 0. And now I can identify my A, my B, and my C for the quadratic equation. Those of you that need a quick refresher, the quadratic equation is x equals a negative b plus or minus b squared minus 4ac over 2a. So I will then go ahead and write that out. We're going to end up with a negative 300 plus or minus a negative 300 squared minus 4 times 46 times 400 all over 2 times 46, and that's going to equal x. So I'm going to simplify this a little bit here. We're going to end up with just simply 300 plus or minus, and then negative 300 squared is 90,000 minus 73,600 all over 92. That equals x. Then we're going to end up with 300 plus or minus 127 over 92 equals x. At that point then, x is going to be two numbers. We get 4.7 and 1.9. Now, and that's due to the plus or minus that we have in the quadratic. The issue that we have is this 4.7. Okay? That is an unrealistic answer. And here's why. If we had x as 4.7, we go all the way back up to this chart. If we were to plug 4.7 in right here, we would ultimately end up with a negative concentration at equilibrium. Therefore, we cannot have that as our number there. So that eliminates this. So this one is not possible. So we're left with just an answer of 1.9 as our x value there. So I take the 1.9, okay, and we go back up to these three statements right here, and we're going to solve those. So we have our H2 at equilibrium is the 4.0 minus the 1.9, and so that gives me 2.1 molar. The I2 at equilibrium is 1.9, or 2 minus the 1.9 to give me just simply 0.1. And then the HI at equilibrium is 3.8 molar. These concentrations emphasize what I was discussing earlier with the chart. Okay? If X is 1.9, you look at these numbers, we have a massive amount of material moving from the reactant side to the product side in terms of our final concentrations. And therefore, that is why we cannot make the assumption X ends up being such a large number that we can't assume X is smaller, so small that it's not going to make a statistical difference when we were to subtract it from the original 4.0 and 2.0 at this step.